introduce Roman Buniy, who will talk about higher order topological invariants from the Chern-Simons section.
All right, thank you, Jason.
Name is pronounced Buniy, doesn't matter. I'm going to talk about applications of higher order linking numbers to Chern-Simons theory. And I just want to make sure that you understand I'm a simple-minded physicist, so don't expect anything deep here. But this work is in collaboration with Tom Kephart, and it ranges from generalizing Aharonov bomb effect to studying effect of boundary terms in classical field theories. And the plan of the talk is to first introduce duality between geometric objects and gauge fields, and then construct higher order gauge fields, and by duality higher order closed curves. Then I'll give you several examples, although they won't go into too much detail as examples, and then I will just finish with demonstrating how expectation values for Wilson loop operators can be calculated in Chern-Simons gauge field theory. So let us start with a general setup when we have two disjoint curves in R3, C and C prime, and suppose the surfaces that they bound, S and S prime, and of course we would like to have some invariant, which would be topological invariant in a sense of as you deform, let's say, when you deform, what do you deform? You deform C in the complement of C prime, the number stays constant. And of course, you can think of intersection numbers between C and S prime, curve C and surface S prime, and you will quickly realize the number of intersection points is not an invariant, but if you would assign signs to them, and if you would sum, and signs being plus or minus 1, and if you would sum over all intersection numbers in a given intersection of two objects, then you will find that this is invariant. And of course, this is a well-known invariant link invariant because it's not only invariant under deformations of C, it's also invariant under deformations of S prime. And you can show that this is precisely the first order linking number. Now, there is a well-known formula using Green's function method, which is given like this. Unfortunately, we won't find any use for this because it turns out to be extremely complicated to do any calculations with it. Instead, we will use the very simple choice of gauge. I will explain what it means, when all we need to do is delta functions, nothing else. So duality. So duality is just a simple consequence of Poincare duality and the Ram theorem, and it states that if you have any one differential one form B, if you integrate over C, that's the same as integral over R3 with some form F, 2 form F. And this F is closed 2 form. And if you want to think the meaning of this it's basically think of this as a delta function, which was a support on a contour C. So whatever happens outside of the contour doesn't matter. This integral gets reduced to B. And by construction, F has to be a closed form. And of course, since R3 is simply connected, you can find a gauge field A. This is a Billian case here. Gauge field A, for which F is a curvature form or field strength form in physicist parlance. And using the, well, that's interesting. Using the Stokes theorem, you would be able to show that this equation, which is the consequence of the definition, can be solved like this. So here's the solution, which might look very counterintuitive, but the meaning of the solution is the following. You choose your arbitrary surface S, which is bounded by a curve C, and you assign for function A of x to be a delta function on that surface, and it's 0 everywhere else. So it's a singular choice. It's a choice of gauge because for physicists, gauge means choice of the surface in this language. And as I said, support of this gauge potential is on the surface S. Now, We will call this a set dual, C curve and closed two form F, but there could be another dual set, so let it be, and some form B prime. Now we can nicely combine the two by choosing this crisscross choice, and we would take integral of A prime over C or integral of A over C prime, and turns out that's the same number. It's a linking number, and we will use this formula. The only reason why I have this formula because we will use this formula in the sequel. And the reason why these two are equal, of course, is because L is C of C prime is the same as L of C prime and C. So clearly, if two form F is closed, then it could be exact, but it doesn't have to be. And of course, the interesting case is when it is not exact. So here's a simple example first, hop link. And what you see here is the choice of surface S1 would be in the plane of slide. And the choice of surface of S2 would be also in the plane, of course, except for the intersection points that you need to take into account. And now the only point where curve C1 intersects the surface S2 would be point like this. This is the point where the curve goes from under to above, if you go in that direction. And using the formula I just displayed, this one, what you need to find is A wedge dA prime, and well, or the other way around by the Stokes theorem. And you can easily see that the only point that contributes to this integral is this point. Is this point P, and because of the choice of normalization, you will obtain that this is 1. So it's a very simple way of proving that hop link is linked. First order linking number of it is 1. Now, if you think about C as a collection of C1 and C2, meaning two-component link, then you can define linking number, well, for n of them even, you can define, of course, you can find that the linking number would be just the sum of these fellows. And of course, if I equal j, that becomes self-linking. I'm not going to deal with self-linking here. This is a subtle point. It requires framing, etc. Subject of the talk is not that. So if I put a little tilde to indicate there is no self-linking included, you will find it's 2, because again, linking C1, C2 is equal to C2, C1. Now, the point now is, let's introduce second order fields, and they would be constructed out of existing geometric objects. So you have a collection of links C1, closed loops, C1 through Cn, and you already have dual sets of curves and closed two forms. Question is, can you construct second order curves and second order closed two forms? Well, you can, and here how it goes. Definition is exactly the same for any one form, B. You have an equality that defines Fij. This is three-space integration. This is curve integration. And of course, this is just the same delta function support.
What does Cij mean? What is second order?
Second order means in the moment it has two indices. That's all it means.
What is Cij?
I will show the expression for it in a second. I will find Cij in 5 slides from now.
And you will find Fij.
And I will find Fij too. It's a dual set, consists of a closed curve Cij and closed two form Fij.
It's a curve.
Definition to be exhibited in 5 slides.
Cij is a curve, or?
Pardon? Cij is a closed curve.
But it has nothing to do with any of the curves Ci.
It does, and I'm going to show how it is. So again,
You haven't given any properties yet that related at all to the initial link.
no, this slide just says this is the wish, and I'm going to define.
Okay, but it could Cij could be Ci, and Fij could be Fi.
Could be, but it is not, because I will show the definition. You asked the question too early.
Well,
Can I continue?
Please do.
Thank you. So definition is coming because the first definition of Fij. So what we want to do is to have definition of a general closed two form Fij given in terms of existing thing. And what is the existing thing? Ai, Aj. two one forms. Now, what can we do with two one forms? Well, we can multiply them, wedge multiply them, or we can take d's of them. Hodge product is not included. Hodge star is not included because it's symmetric dependent, and we want to have topological invariance. Hodge is not allowed. So that's the only possible choice you have here. And I chosen some functions, little f of I, little f of j, and function of g. Now, requirements on fij is that it's closed, and it's closed everywhere, both on curve ci and cj, and in the complement of them in R3. So let's start doing this line by line. First, let's look at the complement. Complement of a union of ci and cj in R3, the fij should be 0. You can show that this necessary condition for this is for g to be constant in the complement, and sufficient condition is g to be just 1. You can look at the details of necessity, but there's no need. So then, thing is to step outside of the complement to look on one of the curves. For instance, how about what is the value of fij, dfij, on one of the curves, ci or cj, for instance, ci. If it's 0, you have this differential equation related on ci. Now, what you can do is this. Let's integrate over the loop ci and see what it gives us. And remarkably, it gives you that linking of ci and cj equals 0. So what do we conclude from here? That the closed form fij, as exhibited here, can be defined only if two initial curves ci and cj are not linked. And this would be a recurrent theme for the rest of the talk. Now, question, of course, is, if it's closed, is it exact? Well, yes and no, depending on the connectivity. We will nevertheless seek solution which satisfy this. So in a way, I'm talking about not local functions, but functions which are global, meaning they depend not only on the value of at a point, but at the history, at the path, which some other functions took, and those some other functions would be gammas. All right, so again, let's require this and look on various subspaces defined by ci and cj, complement and curves themselves, and you will have something like this plus a symmetric combination of that. So what you can find that these quantities gammas, which I had here, they are nothing more than just line integrals of forms ai, of course in the complement of all the curves. And curves I assume to be non-linked, as you already saw. And what remains is to be found is the value of these gammas, not in the complement, but on the other curves. We will never need gamma I on ci, only gamma I on cj. And there are two cases to consider. I will show the picture in a second. If intersection of surface I and curve cj is empty, then you can show that gamma is constant from I guess, this equation. No, this one. From this equation. And then if the intersection is not empty, you say, you write this as a union of disjoint pieces. And here's an example when you have a curve ci being perpendicular to the plane of slide cj, which is the line of slide, and they intersect, and they're intersecting along these straight yellow segments. And so what we're going to do is let's call cjm to be part of the curve, keep an orientation that closes this segment in the curve, that's interesting, in the curve cj. And then we would have something when technology collaborates. Let's
Power plug?
no, but there's no need for power.
Maybe the cable.
Your computer will go to sleep maybe more less often. Seems like the video link has been dropped.
Do you want to try moving and using the power supply from the other laptop?
There it is. You got it.
Oh, there you go.
Yeah.
So maybe it just needs to be, maybe I should leave this on in case I need to come back to that. So, right, so what I was saying, we have these two straight pieces which are intersection of these curves, and don't close, intervals close, and union of these two yellow pieces would be called C prime J. It's in the curve Cj, and the complement of it, meaning the remaining white pieces, would be C J double prime. The point of this is, if you now use those equations we had, you can show that duality, skipping some irrelevant technicality, you would have the duality is written, this duality is written in this form. And this is finally answers the question you asked. What is the definition of Cij? Because this, which is copied here, should be true for any one form B. Therefore, Cij should be this configuration. Now, if you carefully study what this thing is, you would not be as suspicious as you should be at the moment, because you will show that this is nothing more than the commutator path. This is the path which is taken in a group space. It looks like this. AI are generators of the first homology group of the curve Ci and Cj, and you write things like this. Of course, they do not commute, and therefore Cij is a non-trivial path. It contains four pieces. For pieces, you have a fixed point, let's say fixed here, and you have a generator linking with Ci, generator linking with Cj, then you unlink with Ci, unlink with Cj. And then we will have this stuff again. Then what you're going to show, that using the Stokes theorem, you can prove that support of Fij would be only on Cij's, on these commutator path, and the support of Aij would be only on the surface, which is bounded by Cij. So that concludes the definition of Cij's, Sij's, and Fij's that you were so eager to hear. Now, you proceed to the third order linking, third order fields in precisely the same manner, although there are some subtleties. The subtleties are that if you try to use two forms, of course, you don't take AI, wedge Aj, wedge Ak, because that will give you three form, and that's not the thing you want. You want to only have two forms and then use the D inverse to get the potential A back. So turns out there are these two. And you may ask why there is no AIK, wedge AJ. Well, it's a fact. You don't need that. And in order to define this, similar to the second order, you show that there is no link in between the second order curve, now Cij, and first order curve Ck for all permutation choices of ijk, of course, assuming that I is not j. And then, of course, in order to extend this to the full space, you would meet the topological obstructions of the kind that there shouldn't be any linking number, linking of the first order or the second order or the third order, a second order between the curves. And Cijk, careful examination will show you contain 10 pieces, 10 generators, and this is the third order commutator path in the space. And of course, you recursively proceed to higher order and define them in the manner stated above. And you can see the relation of all this machinery to Massey products in the cohomology groups. Now, example of Brownian rings. Can I just use extra 5 minutes due to technology failure? Or that would be not allowed?
Well, take 2 or 3.
Okay.
So we may have to cut questions.
Okay. Okay. So Borromean rings is a simplest example when you can show that there is no linking numbers between pairwise links, and nevertheless the whole thing holds together. You cannot pull it apart. You can show that the first order non-self linking is 0. It's amazing. Self-linking is not 0. And then you proceed to calculate the second order by using the formulas I just showed. And there is your friend, triple wedge product of 3 gauge fields. And if you think about intersection point of all 3 surfaces being chosen for different colors lying in the plane, you can see this is just a point. And that's precisely the point that contributes to this integral, because you have a volume formed here. So you proceed similarly. If you want to find the first non-trivial example of the third order linking number, surprisingly, the answer is that you have to go with the Whitehead link of 2 components. And you can show that the first order linking is 0. You can show that second order is 0. And to count the number of orders, you count number of indices -1. So this is the second order. This is 0. And then you look at the third order, which is 1, 2, 1, 2. And that's non-zero. And then another one non-zero would be of this kind, another is of this kind. and again choosing closed loops as a union of all first-order curves and all second-order curves and third-order curves that can be created in these circumstances. For instance, there is no C111. It's just by construction. You will show that the third-order linking, non-self linking, is actually non-zero. And you can just normalize if you don't like number 16. Point is, if you want to apply this to Chern-Simons theories, because I'm out of time due to cooperation of something, the reason why we use Chern-Simons theory is precisely because non-abelian, because of definition like this. It reminds you the definition of the linking number through the duality. You have B wedge dB for arbitrary one form gauge field B. And skipping things further, you can show that this is nothing else than just self-linking of a bunch of curves densely fill in the space. And what you want to do is now to ask the question, what would be the quantity in a quantum field theory that you should calculate expectation values? That's a standard law in QFT. And turns out it's a Wilson loop operator, again for the reason of duality. It's something that can be easily converted into volume integral by integral C dB of B is integral over 3B wedge dA. So this comes from the Chern-Simons, and this comes from that. And of course, what I used here is that I used that the measure, path integral measure according to Feynman, goes just like that. So final calculation then is you want to calculate this expectation value of a collection of contour C of all orders, and you will find this. Change variables, you got this. The first term is nothing more as a gauge field 0 case. Let's call it the empty set because there are no curves. This is a boundary term vanishes. This term is a self-linking of curves of all kinds. And last term then is if you generalize this to higher order linking, remarkable fact about Wilson loop is factorization property. You write the product of Wilson loop operator can be written as a single Wilson loop operator for the product of the union of all the curves. That's the property. And if you do so, you will calculate that self-linking, which occurs in this formula, meaning expectation value for any collection of curves, closed curves, first, second, etc., nth order, can be written as a linking of CC. But linking CC is graded by first order of the curves and then each curve in the middle. And here is just a list of things you will find. So to conclude, this is the way to introduce higher order linking, and by duality, higher order gauge fields, and by duality introduce higher order curves. And then the challenges which are remaining at the moment is to apply this to non-abelian case, as Witten did in relating to Jones polynomials. The reason why we didn't do non-abelian yet, we did some tiny pieces, is because non-abelian Stokes theorem is not a trivial stuff, although there is formula explicit. And we would like to apply this to studying link polynomials, and for instance, Kaufman polynomial or Jones polynomial. And the reason why it's possible is because if you think about singular support on these surfaces, it plays very well with recurrence relations you use for generating polynomials. If you think carefully about this, where your delta function moves as you swap two lines, it moves off that supporting surface of the surface. Thank you. Sorry for the delay.
So why don't we bring up the next speaker to get set up, and we can have questions while that's happening.
And just a quick one, just that.
Lou was first.
Aluska.
Lou was first. Go ahead.
Yeah. So presumably,